Okay, AP Calcers, now we're looking at 2018 free response question number 4. We were given a table right here of t being measured in years and h of t, which is the height of a tree, being measured here at 5 different values of time here. So h of t is measured in meters, t is measured in years, and select values of h of t given in the table above. Really no important information worth circling, I don't think, here in the text of problem number 4. So let's dive right into part A. This is a pretty typical question. Hopefully you've seen it already. You're certainly going to see it again, I think. Use the data in the table to estimate the value of h prime of 6. Without giving you an explicit definition of what h of t is equal to, you can't actually find h prime of 6, so we can only estimate it by looking at the table right here. And in almost every one that they give you, this x value, or in this case a t value, happens to be directly in between two other t values that were given in the table. 6, you will notice conveniently, is exactly halfway between 5 and 7. So what we're going to do then, everybody, to approximate or estimate an instantaneous rate of change, we're going to find an average rate of change as well. Change in y over change in x, or in this case, change in h over change in t. So to write this one out here, h prime of 6 can be approximated here by doing h of 7 minus h of 5 all over 7 minus 5. Looking at our values in the table, that's an 11 minus 6. All over a 7 minus 5 there, and we end up with 2.5 then for that answer here. So we've done that. That is part of the answer right there, so I should box that up. But it also says, using correct units, interpret the meaning of h prime of 6 in the context of the problem. So if we think about units first, that probably helps more. The h's up on the top, the 11 and the 6, were both measured in meters. And down on the bottom, the 7 and the 5 were both measured in years. So the units we come up with here are going to be meters per year. And that right there really can be useful, I think, in trying to answer this question where it says interpret the meaning of h prime of 6. Meters per year is a rate of growth. So what I wrote here is that h prime of 6 measures the rate at which the tree's height is changing. Make sure to include units here in meters per year. And this last little thing right here is something that I think a lot of people forget, and I do not believe they take off points for that, but it would be nice to specifically say that the value of h prime of 6 measures that growth rate at t equals 6, not just in general. Okay, so that was part A. Question B, explain why there must be at least one time t in between 2 and 10 such that h prime of t is equal to 2. This again is something, a question type that you're going to see a decent amount, and in almost every case that they do that, the value that they chose here was not random. They chose 2 specifically because if we go back and look at the table, we should be able to find, much like we did in part A, an average rate of change here where that AROC is going to be exactly 2. So I was looking for a spot right here where the change in y divided by change in x would be exactly 2. It doesn't look like it here, but right there, everybody, from 3 years to 5 years, that's a span of 2 years, the height increases by 4. And that 4 divided by that 2, sure enough, that's going to get us the 2 right there that we need. So the theorem that usually gets used on a problem like this to prove the existence of a derivative equaling a particular value is the mean value theorem, everybody, which I think we did in section 4.3. Okay, so as we look at part B, let's take a look at what's going on right here. So I went ahead and computed then that average rate of change we just talked about. H of 5 minus h of 3 over 5 minus 3 got us the 6 minus 2 over 2, 4 over 2, and that got us 2, which was the value that we were looking for. So I wanted to use the name of the theorem that I was invoking here. So since the average rate of change of h of t is equal to 2 on the closed interval from 3 to 5, then by the mean value theorem, probably a comma there would have been a good idea, h prime of t has to equal 2 for at least one value of t that's on this interval here from 3 to 5. Now, an existence of that on the interval of 3 to 5, that's also contained in the interval right here from 2 to 10. So it was okay to do it that way. There are other ways of proving this. I've done this in a more complicated way than was necessary in the past, where we do something with the intermediate value theorem, where like this average rate of change would be a 1/2, and this average rate of change might be, but whatever. This is probably the most direct way to do it here with the mean value theorem. Okay, let's take a look at part C here. Use a trapezoidal sum with the 4 subintervals indicated by the data in the table to approximate the average height of the tree over the time interval from 2 to 10. Okay, this is important here because I think a lot of people are going to get focused on the idea that we're doing a trapezoidal sum and think, ooh, I know how to do that, and then realize that we're actually using that as a means to an end. What we really want to come up with is an approximate value for the average height of the tree. So what we're really talking about here is the average value of a function. So let's take a look at what's going on here in my work for C. So the average height or average value of a function, if you recall, is 1 over b minus a times the integral from a to b of whatever function it is that we're dealing with. Well, we're trying to find the average of the height, so we use the height function here as our integrand for h of t. So we did a 1 over 10 minus 2 times the definite integral from 2 to 10 of h of t dt. And actually, this isn't an approximation yet. That really is exactly correct right there. But on the next step down, when it comes time to try to come up with the value of that integral, this is where it really becomes an approximation. So the 1 over 10 minus 2 is going to get us a 1/8. And then what I did here is started coming up with the areas of each of the 4 triangles here. So the 4 trapezoids. So every trapezoid starts with a 1/2. You'll notice I used that in all 4 spots. The first trapezoid from 2 to 3 has a height of 1, and there's the sum of its 2 bases, 1.5 plus 2. And I did that same thing then with all 4 of the trapezoids, looking something like this. And again, don't forget the 1/8 out in front. Okay, so trying to clean up what was inside, I now understand where a question that somebody had emailed me came from. This got to be weird to me, and I got a little annoyed with it, to be honest. For a non-calculator question, I don't know why they felt the need to go with decimals that you then had to take half of. This seems silly to me and overwrought, but anyway, so we've got a 1/8 here. These are the areas of each of the 4 trapezoids independently. Kind of a pain in the butt to add these numbers up, again, without a calculator. Not that you guys can't do it, but it just seems like kind of a waste of time to me. So the sum of those 4 areas, I got a 65.75, an 8 out in front that or 1/8 out in front that I then moved as an 8 in the bottom. And to me, everybody, this is good. In their solutions, they actually went ahead, I think, and divided that out, which just seemed ridiculous to me. I can't think of any reason why you would need to go further than leaving it as 65.75 over 8. So that answer is perfectly good to me, and I think your AP graders are going to look at it the same way in terms of not making you simplify your answers. And then when we got to part D, this was a weird question here. So the height of the tree can also be modeled by a different function g, and here they have given you an explicit definition of g of x. But worth noting right here, the height of the tree in meters is g, so g is another height function. X is the diameter of the base of the tree measured in meters. Okay, this seems like an initial piece of information right here we might need. When the tree is 50 meters tall, the diameter of the base of the tree is increasing at a rate of 0.3 meters per year. All right, some important information right there. According to this model, what's the rate of change of the height of the tree with respect to time in meters per year at the time when the tree is 50 meters tall? This is a related rate problem, and it kind of read like that, but once we dove into it, it actually seemed like a more complicated and to me maybe overwrought related rate problem than we needed to put on there, but let's run with it. So, taking a look at what we know, with most related rate problems, I like to start it out this way. What derivatives do we know, and what derivatives are we trying to know? So, without reading real carefully, I wrote this out, that the derivative of the diameter of the tree with respect to time was 0.3 meters per year, and that happens at the time when g, which is the height of the tree, is 50 meters. In hindsight, and I'll change this in a minute, x is the variable they used here for the diameter of the tree, so I really should have called this a dx dt and not introduced another variable right here with dd dt. But anyway, there we go. And the derivative that we wanted to know, the question is, what is the rate of change of the height of the tree with respect to time? G is the function being used here to measure the height of the tree. So we wanted the derivative of G with respect to time when G was equal to 50. So what we're really looking here, with the derivative we know being dx dt, and the derivative we want to know being dg dt, we need an equation that related x with g. Well, that was the very function that they gave us right here. G of x is the function that relates those two variables. So we started off with g of x right here and just wrote down what the function was. And I thought it was a good idea to make a note right here of what we said earlier, kind of a reminder for me, that x was measuring the diameter of the base of this tree and g was measuring the height. The other thing that was interesting right here is that they wanted to know what was happening here when the tree was 50 meters tall. That's the height. So what we really wanted to do was take g of x, this function right here, and set it equal to 50. Now, taking a rational function without a calculator and trying to solve that would be a little bit of a pain. Lucky for us, and this is very often the case with non-calculator questions, that's one you might have been able just to look at and figure out pretty quickly. When I saw the 100 on the top and when I wanted it equal to 50, I just started thinking, boy, it would be really nice if this was like 100 divided by 2. And sure enough, an x value of 1 makes that happen. So a little note right there that g of 1 would equal 50. Okay, so with that in mind, we were going to go ahead and differentiate all this, but a mistake that I made in doing this, hopefully you guys didn't, with related rate problems, we're always differentiating with respect to t, not with respect to x. So I should not have written my derivative as g prime of x, but I'm taking the derivative of g, but with respect to t. So this derivative becomes a dg dt. This derivative over here, all right, it's going to need the quotient rule in order to do that. So here we go. We did bottom, 1 plus x, times the derivative of the top. The derivative of 100x is 100, but this is implicit differentiation, so that gets multiplied by a dx dt. Minus the top, 100x, times the derivative of the bottom, which is 1, but again times a dx dt, all over the denominator, 1 plus x, quantity squared. Cleaning this up just a little bit, if you were to distribute that 100 in there, and then actually I pulled the dx dt's out in front of all this, you get a 100 plus 100x minus 100x. So those 100x's cancel, and we get a 100 over a 1 plus x squared, and then the dx dt gets factored out, and that can go either in front or behind. All right, so that's where we're at now for dg dt, and the x value we're interested in came from right up here, guys. The height was equal to 50 when x was equal to 1. So we're now going to evaluate dg dt, that derivative, when x is equal to 1 by plugging in a 1 for x right over here, and then the dx dt is the derivative that we were given at the very beginning of this problem, 0.03 meters per year. So we'll get 100 over 1 plus 1 quantity squared times a 0.03. Again, no calculator here, but it's not too bad. The 100 times the 0.03 gives us a 3. Down on the bottom, the 1 plus 1 is 2, squared is a 4, and we end up then with 3/4 for the answer for part D.